do some linear predictions and extrapolations and things like that. But let's talk more about division. We gotta learn how to divide things. So division. So for example, I would like to take a number like 17,231 and divide it by 12. Does 12 sound good? That looks like a reasonable problem. How would we go about doing this by hand? The good old-fashioned long division. How do you guys do that? You draw a little squiggly, right? Who's with me on that? What do you put 12? Left, so 12 goes here. The other number goes here, right? There's some special names here. When we divide, we call 12, that's the divisor, right? What is this number? What do you call that number? What do you call the number that you are dividing? What? Anybody remember the whole divisor, the quotient, the remainder verbiage? What is this first number? Dividend, right? I don't remember it's a dividend with a D in the end or T. That doesn't matter. But you were taught that in like third. That sounds better with a D, right? You were taught that in like third grade or something like that. So that's why you probably don't remember. But the more important thing, the process. How do we actually perform this division? Does anybody want to help me out here? What are the steps in doing the long division? What do I do first? Yeah, 12 goes into 17. So how many times does that happen? Once. So we're going to put a number 1 somewhere over there. Just kind of have to figure out where it's going to be lined up. Now what? So multiply, right? Is that what you were saying? You were saying that. I mean, sure. What was the sarcasm? Well, it's not 15, there's 5. Now, how do you know 5? You multiply the part of the quotient with a divisor, you get 12, and then you subtract. And this is how you get 5. So 17 minus 12 is 5, right? Then we're going to bring that 2 down, 2 falls down, and we repeat the process, right? You guys remember that? No? So 12 goes into 52. How many times? 5 will get you all the way to 60. 5 times 12 is 60. So then 4. So 4 goes here. We multiply 4 by 12 again. That gives us 48. We subtract 52 minus 48 is how many? 4, right? Then 3 comes down, and we'll repeat the process. How many times 12 goes into 43? Anyone? 3. And then we'll go 3 times 12. That is 36. Subtract. We get, looks like a 7. And then you bring the 1 down. And how many times 12 goes into 71? 5. So again, multiply 5 by 12. That gets you 60. And you subtract again 11. Right? So what that means, that 17,231 divided by 12 equals 1,435, and the remainder is 11. Right? That's one way to express that answer. Since whatever that number we get in the end, if it's smaller than the divisor, then that's the remainder. And I'm not going to go into getting the decimals. I don't care about that. I just want to get the answer. What do we call this number? So we got the quotient, and this is the remainder. How's that? Does that ring a bell? The long division? So what we got now is, so this is one way to express our answer. 17,131 divided by 12 equals 1,435 with the remainder 11. Or another way to express this answer is that 17,231 equals the product of the quotient and the divisor plus the remainder. This is actually called a division algorithm, that a number equals the quotient times the divisor plus the remainder. Is that okay? Are you buying this? That 1435 times 12 plus 11 should equal our original number? I mean, if it doesn't, then we're doing something wrong. I can really quickly check that. 1435 times 12 plus 11, yeah, 17,231, right? Another way we express this answer is that 17,231 divided by 12 equals 1435, the quotient, and then the remainder still divided by the divisor. So using the mixed numbers, it actually looks like that. 1,435 and 11/12. So technically, as you probably aware, the remainder is still being divided if you want to get the decimal. So the decimal is whatever 11/12 is. Who's with me on the funky division? That's, you know, what grade you do that? Yeah. Okay. Let me ask you this example. Another example. I want us to divide 1,001 by 11. Why didn't you do that? See what you get. Just using the long division, go through the process, give me the quotient and the remainder. That's really all I need. Just go 1,001 divided by 11. Okay, so how do we do this? Tell me exactly what to write and what to write where. Hmm? Oh, the squiggly? Okay. Okay, 1,001, right? Okay. So then, how do we proceed? So what do we do? 11 and first two numbers, is that going to work? 10, does 11 go into 10? So you have to go further, all the way to 100. How many times 11 goes to 100? 9, right? And then what? Yeah, 9 times 11 is 99. Subtract, we get 1, right? Bring 1 down, 11 goes into 11 exactly once. 1 times 11 is 11, subtract 0. So there's no remainder, means 11 goes into 1001 evenly, exactly 91 times, or 1001 does equal to 91 times 11, the quotient times the divisor. No remainder. Nick, where are you going? Okay, blow your nose. Yes, that's okay. Is that okay? Now, an important part, but rather weird. And I know I'm going to sound a little, well, crazier than usual, but these two zeros in the number 1001 really matter. Do you agree with that? You don't ignore the zeros. You don't think of, well, bunch of zeros, who cares? 1001, same as 11, right? You don't do that. The zeros are important. What do zeros represent, really? If you break this number down, what was that? That's right. So these are your, what is it, digits, or what do you call those? Singles, digits, these are the tens, these are the hundreds, very good, and these are the thousands. So this number tells me that there is a 1,000, 0 hundreds, 0 tenths, and 1 digit, so 1 single. I don't, do you call that digits or singles? Digit, right? Single digit. All right, so I guess both. We can do both. Okay? So this is really very similar to our polynomial notation. 1001, we can think of 1001 as a polynomial. There is 1,000, so it's 1 times 10 to the power 3. 10 to the power 3 is 1,000. Plus 0 times the hundreds, hundreds is 10 squared, plus 0 times tens, it's 10 to the power 1, right? Those are the tens. And then plus 1 single, well, single is 10 to the power 0. As you probably know, anything to the power 0 is 1. So this is kind of like a polynomial notation. Now, I don't really need to write this like that. It's same as saying 10 cubed plus 1. That's still 1001. So if I write it like that, if I write 1001 using those bases of 10, you do get 1001. You don't care about the zeros, right? But we understand that those zeros are there, and they're playing a huge part in what this number truly is. Do you agree with that? If you happen to have a job that was going to pay you $1,001, and your boss was a bit of a dumbass, not understanding that zeros are important, and cuts you a check for 11, you might get a little upset. Do you agree with that? So zeros do matter. Especially when we're going to start dividing the polynomials, we have to represent, oh, we're missing a square term, so really there's a 0 times x squared type of situation. So anyway, so let's try to take the same idea. Basically, if you understand the long division numerically, you're going to do okay with the long division of polynomials. So for example, let's just do an example. So let's say I want to divide 3x cubed plus 4x squared minus 7x plus 1 divided oh boy, I'm going to get myself in trouble. X squared minus 2x plus, I don't know, 5. So again, this thing right here is the dividend. This thing right there is the divisor. Now we can make a little prediction about what's going to happen here. We are dividing a cubic polynomial, that's what this is called, by a quadratic polynomial. Now take a guess. If you're dividing a cubic by a quadratic, what kind of quotient are you going to get? Can you get a quotient that's still a quadratic? Just think about this. Not really, right? Because if your divisor is a quadratic and the quotient is a quadratic, you multiply them, you get something of the fourth power. While you're dividing something cubic. So really, what you're going to get is the difference of these two powers. So you're going to get something to the power 1 for the quotient. So at most, you're going to get something linear. But anyways, let's do the division. So we're going to do the same process. We're going to take your divisor, goes here, then the squiggly, then the dividend goes here. And then we're going to do something very similar to what we did with the numbers. Instead of dividing the entire divisor by the first 3 terms or whatever, I'm just going to focus on the first terms of these polynomials. And I'm just going to divide 3x squared by x squared. Just think about this. What will happen if you divide 3x cubed divided by x squared? Just dividing the first terms. What will that equal? If you divide 3x squared by x squared. What? 3x, because 3 doesn't go anywhere, and then you subtract exponents, you get 3x, right? This is the same as 3x cubed over x squared. So this cancels, you get 3x. So we just divide the first term. So we get 3x. We're going to place 3x in the x kind of a location. So this is going to be our x column. What? Well, since basically whatever I get from the division, so I get x to the power 1, I want to kind of lining up with the x's to the power 1. So I want this to kind of have only x's. I don't want to have mixing the powers. Just like when you do numerical division, you're kind of predicting where the tens and the hundreds going to place and things like that. So now think about what we did with numerical division. Whatever the value we got here, we multiplied with our divisor. So that's what we're going to do. Whatever we got over there, we're going to multiply with our divisor. That gives us 3x times x squared is 3x cubed. 3x times negative 2x is negative 6x squared. And then 3x times 5 is 15x. Well, because again, just exactly the same process. When you start getting these numbers over here, you multiply them by the divisor, and you place them here, and then you start subtracting. So we're doing the same exact steps as with the numerical long division. Those little values that you start getting as a part of the quotient, we'll multiply by the divisor, we'll place them here, and then we'll subtract. So that's where this red expression came from. We got the 3x, and we'll multiply that by the entire divisor, and we got whatever that thing is. Are you okay how we got that expression? The red expression? Okay. Now, when we did numerical, when you get this little number here, what do you do then? What is the next step? You subtract it, right? We got that 12 over here. You subtracted 12 from 17. We got 5. We have 48. We subtracted 48 from 52. We got 4. So you keep subtracting down, right? So this is what we're going to do here. We're going to subtract whatever the top 3 terms and this new expression. I have to be very careful. We have to watch the signs because we are subtracting. So 3x cubed minus 3x cubed, so that goes away. So they cancel. And then again, pay attention to the signs. You have 4x squared minus negative 6x squared. So it's 4 minus negative 6. So it's positive 10. So it's 10x squared. So it basically, it changes the sign. And then we have negative 7x minus 15x. So negative 7 minus 15, what does that give you? Well, 22, but yeah, negative 22x. So this is the kind of the biggest difference between numerical division and polynomial division, that you have to really pay attention to your signs. You're subtracting the whole thing, so the signs change all along. Well, then repeat the process. Bring the 1 down and do this whole thing again. Take the first term, 10x squared, divide by the first term of your divisor. So 10x squared divided by x squared. What is that going to give you? Just 10, right? So the 10 goes all the way up here. And then we'll repeat the steps. We'll take 10 times the divisor. That gives us 10x squared minus negative 2 times 10, so it's 20x, and then plus 50. We're okay how we got that? Just multiplying the original divisor by whatever the number we got in the quotient. So then do the subtraction. 10x squared minus 10x squared is gone. Negative 22 minus negative 20. So it makes it negative 22 plus 20. So it's negative 2x. And then 1 minus 50 is negative 49. And this is what I was telling you. Our quotient is going to be most likely linear. And that's what it is, right? Power 1. And our remainder is always going to be less than our divisor. Otherwise, you can keep dividing. So we got the quotient here is, this is the quotient. And this is the remainder. So basically what this tells me that 3x cubed plus 4x squared minus 7x plus 1 divided by x squared minus 2x plus 5 equals, so that's dividend, divisor, equals the quotient, which is 3x plus 10. That's the quotient. And then the remainder is negative 2x minus 49. Or, using the division algorithm, I can express the same answer, and this is how we're going to be writing our answer most of the time, equals the quotient plus the remainder still divided by the divisor. Just like numerically. Remember how we did that? The quotient and then the remainder still divided. That last thing that we wrote numerically. Let's try this example. I want to take x cubed minus 8 and divide it by x squared plus 2x plus 4. So the divisor is x squared plus 2x plus 4. Now, the dividend is x cubed minus 8. It's missing 2 powers of x. It goes from the cubic all the way to the constant. So there is no squares, there is no just x. So it is a good habit to write those with zeros. 0 is x squared plus 0x minus 8. Just like with that 1001, we want to have things lined up. This will keep track of all the powers. It is just helpful. When you do the long division this way, it's not an end of the world if you don't put those zeros. It'll just make it a lot easier. There is another form of division that we're going to study next section, and it's absolutely crucial to put zeros there. It makes your life, the process goes a lot faster, but if you miss the zeros, you're going to get the wrong answers, period. Here, if you don't put the zeros, you can still get the right answer. It'll be a little messier. But anyways, so put the zeros for the missing powers, and then do the same thing we just did. Take the first two terms and divide one by the other. So x cubed divided by x squared. What does that give you? X. So we're just going to put x where the x's are. So it's one of the usefulness of having 0x in there. It lines up your variables properly. So then we're going to take that x, multiply by the divisor. So this gives us x cubed plus 2x squared plus 4x. And then we'll just subtract. So that makes it easy to subtract if you have those powers lined up like that. It's another benefit of having those zeros. So everything is lined up. It's easy to subtract, combining like terms or whatever. So x cubed minus x cubed, that cancels. 0x squared minus 2x squared is negative 2x squared, right? And then 0x minus 4x is negative 4x. Bring the negative 8 down. Are we okay how we got to this point? What do I do next? Yeah, so again, just divide the first terms. So negative 2x squared divided by x squared is what? Negative 2. So negative 2 goes here. Then we'll multiply negative 2 by our divisor. We'll end up with negative 2x squared minus 4x minus 8. Right? Negative 2 times the divisor is negative 2x squared minus 4x minus 8. So when you subtract, everything cancels and we get 0 in the end. So no remainder. That actually means that x squared plus 2x plus 4 is a factor of x cubed minus 8. And we kind of knew that, because x cubed minus 8 is the difference of cubes, and if you factor that, you do in fact get x minus 2 and x squared plus 2x plus 4. But for now, this is one way to express that answer. No remainder. Figure that? Now, of course, if you noticed that x cubed minus 2/8 is something factorable, we could have avoided all that mess altogether if you recognize that x cubed minus 2/8 is the difference of cubes. And you factor that as such, x cubed minus 8 divided by x squared plus 2x plus 4. X cubed minus 8, using the difference of cubes formula, gives you x minus 2 times x squared plus 2x plus 4. Denominator stays the same. Then you can see how that whole thing just cancels and you're down to x minus 2. Well, because I'm an evil asshole. What kind of a question is that? Okay? So what I'm trying to say, if something factorable, you might want to see whether you can cut down on the long division. But basically what I just did, I proved to you that that's how, in fact, x cubed minus 8 factors. It factors into the product of that and that. That's another way to almost derive a difference of cubes formula through the long division. So kind of look out for that, because I can give you this kind of example. I don't know, 12x to the fourth minus 8x squared plus 16x, and I want us to divide that by 4x. There is no reason for me to go through the long division, because clearly I can factor something out of here, right? What is the common factor in that dividend? Yeah, I can actually pull out 4x, and that is 3x cubed minus 2x plus 4, and I am dividing it by 4x. What do you think the answer is? Do I need to do the long divisions? Yeah, the 4x cancel, so you're right. So you just get 3x cubed minus 2x plus 4. So if you can see that something factors, of course you can avoid the long division. I mean, if I do the long division, I'll still get the same answer, okay? But really what you're doing, another way to think about this problem is 12x to the fourth minus 8x squared plus 16x divided by 4x. It's really, you're just dividing each term by 4x. You'll get 12x to the fourth over 4x minus 8x squared over 4x plus 16x over 4x. You're dividing each term by that. So that gives you same thing, 3x cubed minus 2x plus 4. So it works well in this type of scenario. Is that okay? Okay. Well, let's do, sure. Okay. Let's try something like this. What if, for whatever reason, we're trying to divide, and I really don't know what's going to happen here, but it's, let's say, x to the power 5 minus 3x plus 1 divided by x plus 7. So how do I set this up? X plus 7 goes here. What do I put on the inside of that squiggly? What do I write here? Right? So yeah, again, if you don't do this, not the end of the world. It's going to be a little harder for you to keep track of the like terms. So it just makes the work a little cleaner. Now, of course, if I were doing x to the power, instead of 5, but 35, you probably have to suck it up and just kind of keep track of all the powers in your head. Otherwise, it's too many zeros. But I won't ask anything. But all right, so let's do this thing. I'm going to go through this a little faster. Just dividing the first two terms. what do we get? X to the fourth. So x to the fourth goes here. We multiply, we get x to the power 5 plus 7x to the fourth. So when you subtract, we'll end up with negative 7x to the fourth. Right? You bring another one down. Again, makes it a little messy, but we'll repeat the process, gives us negative 7x cubed. Well, yeah, I'm dividing the negative 7x to the fourth by x. So that gives me negative 7x cubed. You multiply back, you get negative 7x to the fourth minus 49x cubed. Things about to get really big really fast. We subtract, so the 7x cubed fourth minus negative 7x fourth, that cancels. Then you have 0 minus 49, so it's negative 49x cubed. Is that okay? Oh, no, it's not. It's positive 49, right? Why is it positive? Because we're subtracting negative 49, so 0 minus negative 49 is positive 49. Now another 0 falls down. Repeat the process. 49x cubed divided by x is just what? 49x squared. Multiply again. So it's 49x cubed plus, well, this is going to get really big. What is it, 343? Is that right? Subtract, we get negative 343x squared. Is that right? Then divide again. It is negative 343x. Bring the negative 3x down. And multiply. So we're going to be subtracting, so we will get negative 343x squared. Woo. So 7 times 343 is 2401. Is that right? So you might have to do some long multiplication as a part of the long division. Okay. So then you, again, 343 cancel, then negative 3 minus negative 2401. So that makes it positive 2398. Is that right? I don't feel like multiplying that by 7 any longer. So you divide again, so that's positive 2398. Multiply. There's a 1 that's coming down, so it's 2398x plus whatever 2398 times 7 is. Yeah, all right. 16786. So you subtract, you get negative 16785. Whatever on earth that is, that's our remainder. Got kind of ugly, out of hand. But we could have, again, we could have done without putting zeros here, which would be a little more awkward. At least things are lined up in a more fashionable way. Questions how we did all that. I mean, we just repeated the same process 1, 2, 3, 4, 5 times. We just keep going over and over and over again. Same type of operation. Is that okay? Want to see something cute? Nick? Sure. All right. Let's say you have a function. Remember your functions, the function notation? And that function is whatever that dividend is. Okay? Now I'm going to pick a number. So I'm going to pick that number. I'm going to take a closer look at the divisor. And I'm going to ask you which number makes that divisor 0. Which value for x will turn this divisor into 0? -7. You all agree with that? Well, now I'm just going to take -7 and plug this into this function. So that becomes -7 to the power 5 minus 3 times -7 plus 1. And I bet I can beat you to the answer if you want to compute this on your calculator. I'm going to cheat a little bit. It's going to be a -16,785. Now try this on your calculator, see whether you agree. What? What, this one? Then you lied to me before. Well, let me see. All right, let me take out my calculator. Who's right? Is that right? Yeah. So if I do -7 to the power 5, it's whatever that is. And then I can do the rest. It's -3 times -7 is +21 and then +1. Yeah. Right? There's a little theorem in algebra that connects the value of your function to the values of the remainders. See how those are the same? It's really cute. If you're lucky, we might cover that in college algebra, why that's true. Now this, what? Just gives me the remainder. That's why I got that answer so fast, because I knew it's going to be the remainder. I didn't have to go through the, operations. So anyways, all we need now is to do the division. Okay? We need to learn how to divide, and that's about it. So that's what you're going to do now. You're going to divide.